Hi, Anthony.
Tony
Hi,
P, what's
Anthony.
good?
Alright, so what do we have to do first if we're looking for linearization? What's my plot?
Find a derivative.
Find the derivative.
Secant squared of 1.
Yep, secant squared x.
You're freaking orange.
Okay? What do I do with the derivative?
You plug in negative 5/4.
Yep. So go ahead and do that now.
Why negative?
Because that's what it is. That is the original value.
I thought he said 5/4.
Yeah, same here.
That's why I
It
asked.
sounded like.
Guess what?
Well,
That's fine.
well, it says pi.
No, actually it's 7.
Oh.
5 when it works. I'm sorry.
I don't know.
How do we do?
That's like. Oh wait. That's,
Negative pi fourths would be down 1
that's
from.
2. Yeah.
So whatever you do, secant
Yep.
squared.
So it'd be, think about it, it's root 2 over 2, but it's secant squared, so you have to flip it, so it's 2 over root 2, but then it's squared.
So it's 4 over 2. So it's 2.
Yep, so it's 4 over 2, which is 2. Did we all follow that, or do I need to write out like all the math that went with it?
Yeah, I think I did it.
What
is secant compared to like?
Yeah, it's, so this is really like 1 over cosine squared.
Okay.
Yep,
Wait, so you just square
yep.
It was 1 over square root of 2 over 2 squared.
So that would become 4, or I mean 2 over 4,
and then it's 4
but
over
because
2,
it's,
so
yeah.
Okay.
My goes back up there. What are we missing from this problem?
The y value.
Half of x.
Value. So we need f of negative pi fourths also.
Negative
A
1.
tangent.
So yes, we need the tan of negative pi fourths. So in that quadrant, all students take calc. Therefore, the tan would be
Negative 1.
Okay. Okay, that's good. So then we can
so your linearization would be L of x is approximately. Yep. So if you added that word over to here, it's negative 1 plus f prime of a, which is 2, x minus
minus the
minus and minus, so yeah, so it would become a.
plus
Yeah.
We want to approximate it at negative pi fourths plus 0.1.
It's easy. Just plus.
So it's
2.1.
Yeah, but what?
Oh wait.
You have a negative pi fourths and a positive pi fourths,
I'm gonna actually write that one.
so they cancel.
Negative.
That'll probably be helpful. So you get negative 1 plus 2 times 0.1.
Negative 1.
Perfect. Taking this into account, we have the extension question. If f prime of x decreases on the interval negative pi halves less than x less than 0, is the approximation we just received less than or greater than the actual value?
Well,
Justified.
it'd be concave down, so it would be.
Okay, so how would you write that? How would you prove it was concave down? What do we need to know in order to say
f
that?
prime of x is decreasing in the intervals, so that means that f of x is concave down over there.
What do we know about the second derivative then?
That it would be negative?
No,
Yes.
it'd be
So the second derivative would be less than 0. Therefore, f is concave down. If f is concave down, our approximate is going to be what? Bigger or smaller than the actual? So we could say that since the second derivative is negative, f is concave down, so the linear approximation of negative pi fourths plus 0.1, which is approximately negative 0.8, would be greater than f of negative pi fourths plus 0.1.
Again, how do we know f prime is decreasing?
wait, isn't it the opposite?
So
Nope.
Because isn't if it's concave down, isn't the approximation underestimating?
It's an overestimate. Concave down means your line's above.
Oh crap.
It's okay. You have to be specific, though, about the interval given. Why does that interval make a difference? Is the tangent derivative always going to be decreasing?
No.
No. So again, it has to do with the quadrant that we are looking at the value within. So if we were looking at the value in a different quadrant, we could have underestimates instead. So you have to be very, very particular. If you wanted to know what this graph would look like, think about the tan in general. You have your asymptotes. Anybody recall the values the asymptotes are at?
Negative. The pi or pi? And pi.
So here would be my 0. Do you see how the graph is concave down from negative pi halves to 0? But it would be concave up from 0 to pi halves. So because negative pi fourths would live in here, we're talking about this tangent line right there. Those are the types of things you need to be able to interpret and justify. This is a justification that they would expect for this answer. You would have to describe the second derivative, knowing what happens on the first derivative to get you to what's happening on the original to justify this. The graph means nothing. I just give you the graph so you can see it. The words are all that they would accept.
So why do you exactly need to state that the second derivative is negative?
Because the way the derivative tests apply themselves, it's not enough to say that f prime is decreasing. The second derivative test says you have to show the second derivative is negative. It's because there are times where you could be non-existent on the second derivative, but potentially decreasing on the first. For a function that's like irregular, you know what I mean?
Yeah.
So I think that's where the justification is truly coming into play. All right, let's continue to the next part of our notes. I think I stapled your notes, Goofy. So Newton's method in your notes is the last 2 pages. Just kind of go to the next page. Sorry about that. Okay. Newton's method, by definition, is a numerical technique for approximating a zero of a function by finding the zeros of its linearizations. Our calculators use Newton's methods when you hit second trace and you go to the zero feature. Our calculators use Newton's method, so you go to second trace and use the zero feature. So this is your definition for Newton's method, guys. It's not written at the top of your page. So where it says Newton's method, semicolon, you would write a numerical technique for approximating a zero of a function by finding the zeros of its linearizations. A numerical technique for finding the zeros of a function by finding the zeros of its linearizations. So this is a graphical, again, representation of Newton's method. So we have no idea what that blue function is. We just know that it's some function that we could definitely say has a root. We can clearly see it crosses the x-axis. So if it hits the x-axis, we know that it has a root or a solution. Therefore, it is also differentiable because it is continuous and has no jumps or discontinuities that we can see on this interval. So let's say we pick some point on this screen clipping. So we're going to pick this point x1. What we want to do is consider the tangent line to the graph at the point x1. So that's what we've been doing. We've been considering a point on a graph and finding the tangent line to that point on the graph. So we've been looking at points and finding their tangent lines. This would be an underestimate because the graph is concave up. So if we were to just simply look at what we've been looking at with linearization, our linearization would be the green line. It would be an underestimate because the graph is concave up. Now, let's suppose that this tangent line crosses the x-axis at x2. So what we did is we took the tangent line we found in green. So we took our linearization function and we found its x-intercept. We used that x-intercept value, x2, and we're going to find a new tangent line to the blue curve. So do you see what we did? We picked a point, got its linearization, we found where that point had an x-intercept, and we're going to find its linearization. Hence the new green tangent line. What do you notice about the tangent line to x1 versus the tangent line to x2? What's happening? It's getting closer and closer to the actual root of the function. So what we're doing is we're going to take this x-intercept here again, and we're going to find another tangent line. And we're going to do it again. And we're going to keep doing it until it appears that my tangent line goes through the root. So we're going to do it an nth number of times, creating this new function y minus f of x to the n equals f prime of x to the n for x minus x to the n. And our goal is to make the y value 0. Because when y is equal to 0, what do we find? The x-intercept, or the root. Yep. So to see where the line crosses the x-axis, we continuously set y equal to 0 and solve for x. Every time we do that, we're going to get closer and closer with our tangent lines. The formula is x minus x to the n equals negative f of x to the n over f prime of x to the n. The formula. So don't write this in that, like, now we're actually going to derive it, but you can put this, like, on the side of the box. So we're going to manipulate it even a little bit more. Because when do we ever really keep two things on one side of an equal sign? So the last implication would be to move it over, but you could keep it where you are. We're going to derive this anyways. So what this does is this creates the tangent line where it would cross the x-axis through the x-intercept. Mm-hmm.
So why wouldn't we just find the tangent line at that x-intercept point?
Because let's say we have no idea what that x-intercept point is. So think about how on number 3 for the warm-up, I let you use your graphing calculator and find the root. So you got that really crazy decimal, like 0.5, negative 0.567 or something. So you can't approximate that right off the bat. But maybe if you saw the graph like this and you had those numbers, you'd be like, oh, maybe it's close to like negative a half. So what we would do is we would make our x1 value negative a half. And then what we would do is we would find its linearization and then set the y value equal to 0, and we'd get that it's that way a little bit more. So then you do it again and again. So everything we're going to do with Newton's methods, for the most part, on the graphing calculator. Unfortunately, Newton's methods on the fit test, and guess what you don't get on the fit test?
So this is on the fit test?
Newton's method is on the fit test.
No calculator.
No calculator. So we have to learn how to do these without a calculator. So obviously the functions without the calculator aren't going to be gruesome functions. They're going to be functions that give you like integer roots. But again, the assumption is that you have no idea what it looks like on a graph, because they're going to give you a function and you have to figure out what the root would be for that function. But it's like not going to be a factorable function or a quadratic function. So let's go through the process of deriving kind of where this comes from, because it's more helpful to see where it's derived than it is to simply just give you it. So let's start by assigning ourselves the tangent line. So what we want to do is we want to say, okay, let's find the tangent line from the very beginning. So we have the point on our tangent line, x to the n, f of x to the n, and we would look at the slope of that point. So we would look at the derivative of x to the n for our slope. So we'd use our tangent line and point slope form. So you would have y minus f of x to the n equals f prime x to the n times the quantity x to the n minus x. The only thing we want to change is that in order to find the roots, what do we do to the y value? To find the roots of any function, what do we do to y? Set it equal to 0. So if I said, here's the equation of your tangent line, find the roots of that tangent line. Why not, honey? Oh. Yeah. I was jumping ahead. Thought. Thank you. Okay, find the roots of the tangent line. So in order to do that, we're going to set y equal to 0 and solve for x. So if I wanted to get x by itself, what would you probably start by doing?
Divide by f prime of x n.
last thing we'd have to do to solve would be to add over the x to the n.
You keep the negative, right? On the bottom, on the left side.
Be cautiously aware that this f prime of x to the n isn't under the x to the n. This is like a whole number minus a fraction. In terms of words, what does this represent? We just kind of looked at it graphically in that interpretation. What would this represent? The x-intercept of the tangent line. So again, just we want to make sure, right, you understand this formula here would give the x-intercept, or the root, of the tangent line. You could continue that process so that we would create a new x to the n plus 1 for x to the n, and continue until we found the actual root. So what we're going to see graphically on our calculators is that it will start repeating these crazy long decimals. The PIT exam, and even there's maybe 1 or 2 newtons that pop up on the AP test every once in a while, they might only ask you for x to the 2. So you only have to do it twice. You're not going to necessarily find the root like we do on the calculators. They might only ask you to do this process twice. So they'll say, okay, what's n of x to the second? So you just do it twice and then get your approximation. So let's look at number 1. It says, use Newton's method to find all the real solutions to the function f of x equals x squared minus 5. And then it says to 6 decimal places. So we're going to do it kind of like the long way to start until our numbers get gross. And then we're going to do it on the graphing calculators and show you how you can use that as your trick. So what do I need pretty much any time? I'm going to do a linearization, Newton's method, differential problem. I need the derivative. So what's the derivative of x squared? Okay? And this problem doesn't exactly tell me the roots, now does it? What do I know about x squared minus 5, though?
It's going to have one between 2 and 3.
Yeah, it's going to have 2 roots, right? Because it's shifted down 5 units. And then we know it would be at 1 and negative 1 at negative 4. And then we know that at 2, it would be up 1, 2, 3, 4. So it's over here at negative 1, which means by the time we got to 3 and negative 3, it would have crossed our x-axis. So that means that our roots are between 2 and 3 or negative 2 and 3. For the sanity of our end problem, let's pick the root between 2 and 3. Because if we pick a negative, all we're doing is adding negatives into it, and we know that they're just going to be opposites of each other. So maybe we predict that the root is at 2. So what we would want to say is, okay, our prediction, or our x to the n that we want to start with, is 2. So instead of calling it x to the n, we're going to say n is 1. So our x to the 1 is 2. So think about the formula that we just constructed. Our formula is x, and this is why I kind of wrote that n the first time. It's x to the n plus 1. That's going to be the outside. That's what it's equal to. Because it's going to equal the next root that we're looking for. So our formula is x to the n plus 1 equals x to the n, which we said was 2, minus f of x. So that means I need to know what's the value at 2. So what is f of 2? So it's minus -1 all over f prime of 2. So f prime of 2 is, so again, you see how you could actually do this analytically, meaning without a graphing calculator. So I have 2 minus a fourth. So that gives me 2.25. 2.25 represents x to the n plus 1. Or x2, because n was 1, so 1 plus 1 is 2. So now what we want to do is we want to find x3. So what you do is you replace this number here with 2.25 every time. So it becomes 2.25 minus f of 2.25 so 2.25 as a fraction is probably going to be easier to square than as a decimal. So 2.25 as a fraction. Thank you. 9/4 squared would become, and what are we subtracting from that? 5. So, go ahead. Is it 20 over 40? Are you saying that? Yeah, because what you're going to do is just multiply 5 by 16. So 16 times 5 is, yeah. So you get 160. Is that what you said?
I just simplified it.
God, I was like,
I didn't like equal denominators.
that's what I was trying to figure out. I was like, so I don't think he said it wrong. I just think he said it and I didn't hear him. So you get 116. So that's your numerator, because that's f of 2.25. And we have to put that over the derivative of 2.25. So 2.25 times 2, or you could say 9/4 times 2, whichever one you want. So you could have it as 18/4, or you could have it as 18/4, because again, 9/4 times 2. It's easier to keep it as the fraction because now we can get rid of the fraction and fraction. So flip it, flip it. Yeah, 8 times 9. That's where pretty much on the pit test you would stop. They typically have you do it twice. This is where I would tell us to get out some calculators to finish it, because that's not our root. Oh, so let's see. You'd have to multiply 4 by 18, so 9 times 18. Well, 972. So stop putting our brains with the fractions. Get out your calculators. I want to show you how to do it on this. So here's what you want to do on your calculator. Which I didn't put out the notes for you. You want to, in y1, enter the original function. So in your graphing calculators, in y1, go ahead and enter x squared minus 5. In y2, I want you to enter the derivative. So in this case, our y2 would be 2x. And then you're going to hit second quit and go back to your home screen. What we're going to do is we're going to store our guess into x. So let's go back to our x1. And what we're going to do is we're going to hit 2 on your calculator. You're going to hit the STO button at the bottom above the on. So you're going to hit STO. And then you're going to hit the X. And then hit enter. What? So what that did is that stored X equals 2 into your calculator. What we're going to do now is we're going to type out our formula. So our formula would be X. So you're going to hit the X key again on the calculator. Minus parenthesis. What's the numerator of this formula? F of x, which we stored into y1. So hit vars, which is below the arrowies. Go over to y vars. Hit function. And then you see how y1 is the first option? Hit enter. Then we're going to divide it. And then we're going to go back to vars, back to y vars, back to function, and then we're going to hit y2. Close those parentheses. And if you hit enter, look what we get. Here's what I want to teach you, the tricks of the calc. This became our what? So what you want to do is hit the STO key again. So it should say ANS, arrow. Hit the X button. So you want to hit ANS, hit the STO key, hit enter. Oops, I wrote down X. And what it's going to do is that's going to store that as your new X value. Hit second enter, second enter. Do you see how it brings up the x minus the y1 over y2? Hit enter. That gave you this decimal that I was like, yeah, we're not figuring that out.
Good deal.
Hit STO. Hit X. So now we're just going to repeat these steps.
Second enter just brings up the equation.
Yeah.
Second under again. Brings up your equation because it's like going back to that.
So what I want you to do is you're going to repeat this process again until your answer repeats twice. So this represented what? X3. So you on your paper, and again it says 6 decimals, so my repeating covers my bum. So you have 2.2361. What's X4?
Almost have an exact one.
I got one word.
My last number is 8 on the one before, and now the last number is 7. Oh, jeez.
So X4, you get 2.236067. Store it. Do it again. X5. You got 2 duplicate answers to 6 decimals, you're done. This is your approximate root. What do we know about this root? We know that it occurs at the positive and the negative. So we would know that the root would be plus or minus 2.236067 approximately. Mm-hmm. Let's look at the next example.
I'm using a calculator on the next example.
I want to do at least x1 and x2 individually, so I want you to try to predict where the root would be, and then we'll go from there. So we have x cubed minus x plus 1. So what's your derivative? So think about x cubed. How many roots should that have?
3.
Okay, so it could have 3 potentially, which means it could have all 3 reals, or 1 real and 2 imaginary. So we know imaginaries have to be in sets of 2. Do you remember the rule for how you could look at the roots? Your p divides q.
I don't know what that means.
So it's the first number and the last number, and you divide them by each other. So we have potential roots at, if they were integer roots, at 1 and negative 1. So which one do you want to go with? Let's do negative since we didn't do a negative the last time. So we're going to make our x1 negative 1. So that means that I need f of negative 1, and I need f prime of negative 1. So if you plug in negative 1 cubed is?
Negative 1.
Negative 1 times the negative is a? Plus a?
5. You're trigger happy.
Okay.
What makes you say that?
So we get a 1. The derivative at negative 1? Negative 1 squared is 1 times 3 is
3.
minus 1 is. So x2 would equal x1 minus f of negative 1 over f prime of negative 1. So you have negative 1 minus a half, so we get negative 3 halves. So that means my root was a little bit more to the left than what I thought. To plug in negative 3 halves, we're going to get kind of gross. So let's jump to the calculators now. So what we would be looking at is negative 3 halves minus f of negative 3 halves over f prime of negative 3 halves. I could hear it. How'd you know it was yours?
My family.
I don't know where my phone is at the moment. Probably somewhere on my desk. So go to y equals, plug in the function for y1. So what we're going to do is we're going to put this right here into y1. We're going to put the derivative into y2. Clear out your home screen so you can see it all fresh and anew. Okay, so then we picked our x1 in this case to be negative 1. So you would hit negative 1, STO, x. Hit enter. And then, do you need me to tell you how to get back the formula and everything? So it would be x minus parentheses vars. Go over to y vars. Hit enter on function. Hit enter on y1. Divided by, and then hit vars, y vars, function, y2. Close your parenthesis. Hit enter. And you get the negative 3/2 like we got. Then what you're going to do is hit STO, X, enter. So it just shows like the negative 1/2 line again. Then you're going to hit second enter, second enter, and it should bring back up the x minus y2 over y1, or y1 over y2 rather. Hit enter, and we get x to the 3 is negative 1.347826. Hit STO, X, enter. Second enter, enter. And we get x4 is negative 1.325200. AP says cut your decimals, like you don't have to round them, so you just cut it 6. Hit STO-X, enter. Second enter. And we get x5 is negative 1.324718. So we still haven't repeated, so we got to do it again.
Might go to the next step.
Yeah, I think
This is a dangerous game.
You have to cut it to read it.
Cut.
it gave me the same thing.
Oh, yeah.
It's done it.
There will be a calculator question on your test on Tuesday.
One.
Hey.
Well, like this. Like I'm saying, there will be one like this.
This is not bad. This is sufficient.
Okay, tomorrow we'll do differentials. So tomorrow is, what, Friday?
Yeah.
So we'll do differentials period 1, and then we'll start reviewing for your test period 3, and then we'll review for your test Monday and Tuesday periods 2 and 3, and then your test will be Wednesday. Again, primary focus of the test is going to be on Newton's methods, linearization, and graphing curves. So it's a unit test on those 2 topics, plus we tested, we didn't really quite test on MVT, IVT, or EVT yet. So those theorems are going to come back into play too. Tuesday. In the book, we are on page 243. You're looking at 11, no, we did 11 and 12, just kidding. 15 to 20.
Oh, Jesus.
They are calculator problems. 15 to 20, all calculator problems. I need to have the x's wrote out, just like we had the x's wrote out in our notes. Some of the functions have multiple roots. Let me find 2. So 16 has 2 solutions. 17 has 2 solutions.
So as soon as we get to like the calculator portion, is that when we can just put like x cubed or like x?
So pretty much our whole homework's going to be calculator ones because it does. Our textbook
Like as soon
isn't
as you get
set
to
up.
x2, it's like,
Yeah, like I just want you practicing X1 for your own well-being because there will become a pit test at some point that you have to do it that way. But the AP is all, the Newton's method is always on the calculator. But like I said, I have to show both because we're kind of mixing the 2 in here. So.